What's being illustrated in this animation is the definition of the derivative. In other words, how can we get the slope of the tangent line, which we call the derivative of the function at that point, from 2 points on a secant line? And the secret to doing that is to use a limit. So if we just focus on this little piece right here, this is telling us that as delta x shrinks towards 0, delta y over delta x, which is the slope, is going to approach the slope of the tangent line. And so we can look at delta y over delta x mathematically in a few different ways. And there's two primary ways that you'll see the derivative defined. One is going to be something that looks like this, and the other is something that looks like this expression right here. So let's just get ourselves oriented on the graph here first. This is delta y. This is y2 minus y1. y2 is the value of y for the x value of x. y1 is the value of y for the x value of a. So f of x is y2, f of a is y1, x is x2, a is x1. So this is basically just the old slope formula that you've used a long time, only with function notation. So this allows us to plug in any function that we want here and to generalize the calculations and the formulas here. Now another way we can look at this is by saying, rather than having points with different names here, why don't we just use the fact that we're changing our delta x. So if this point is a, where we want our tangent line, this point will have an x value of a plus delta x. And we're going to change delta x to h just to keep the notation a little bit simpler. So h and delta x are the same things. So once again, at a, our function value is f of a, and at a plus h, our function value is f of a plus h. And so once again, we have y2 minus y1 over delta x. So x2 minus x1 is already basically collapsed down into this thing that we're calling h, which is just delta x. So delta y on top, delta x on the bottom, and we want delta x to shrink to 0, or in this case we want h to shrink to 0. Notice that over here, in order to get delta x to 0, we want x to approach the same value as a. When x and a become the same thing, they would be 0. So the limit is telling us that x should approach a, or that h, the difference between those 2 points, should approach 0. Let's look at an actual example. We're going to take this function x squared, and we're going to find the value of the derivative at a equals 1. So we're going to be looking for the slope of this tangent line when we have a is equal to 1. Right now I've got x also equal to 1. So the 2 points are the same, and as we've seen before, our slope calculation is 0 over 0, which gives us an undefined value. If I move away a little bit, okay, if I have a equals 1 right here, and my h is 0.08, this is my delta x, remember, so then my x value, my moving value, is 1 plus the 0.08 is 1.08. So these two things are really telling me the same story. And as I move that point back and forth, you can see the green secant line approaches the tangent line. And you can also see that as I get very close to h equals 0, or x equals 1 in this case, my slope calculation seems to be approaching a slope of 2. So let's go ahead and sneak up on that from the left. Watch down here. Okay, I'm at my smallest h value, negative 0.001. I'm almost at 2. As I go one more to h equals 0, then I get an undefined slope. I'll go one more past that, and my slope calculates to 2.001. So again, it seems reasonable that my slope at that point should be 2. Now I can also move these points anywhere I want. We can try this also at maybe an x value of 2 in this case. And the idea is going to be the same. As I get close to 0 here, I get an undefined slope, but I can move this one way or the other. If I'm a little bit to the right with my second point, my slope is 4.002. If I'm a little bit to the left, my slope is 3.999. Again, seems like a slope of 4 is reasonable. Let's look at the calculations here so we can understand these formulas a little bit better here. So once again, I have 2 points, and let me move them apart a little bit more so they're really easier to see. So my target point is a equals 2, and so f of a is going to be whatever f is when I plug in 2. And so since my function is x squared, if I plug in 2, I should get 4. My f of x value is whatever I get when I plug in my x. So x is 2.205. Let's make that something a little bit less nasty. 2.2, if I square that, I get 4.84. So this is y2 minus y1, and delta x is the difference between a and x, or it's the same as delta x, which is h, 0.2. So doing that calculation gives me 4.2. So we can do the same thing looking at this a little bit differently. These two things are really going to be the same. In other words, I'm just calling x a plus h. In other words, x is h units to the right of a, and so if I take a and add h units, I should get x. So a plus h is the same thing as x. F of a is not changed, and the only thing that's changed here in the notation is that I'm using h, which is delta x, instead of calculating delta x as x2 minus x1. So that's really what's connecting these three things together. And then as I take the limit of that, I get the actual thing called the derivative, which is the slope of the tangent line right at the point, and that's what this notation down here is telling us. This might be a little hard to read on the video, but you can go to the app and see the full text. This is really showing, these two are showing the same thing that's on the app in terms of calculating the value at a particular value of a. We can also say, well, what's the value at any point x? And we can just change a, which is a number, to x, which is going to be a variable. And we can generate what's called the derivative function, which is what we're going to be spending a lot of time in the first semester of calculus calculating what we call the derivative of a function.